Hi. In part one, I talked about The Lord of the Rings for a while, but also talked a little bit about how we could use data on an object falling to determine the distance an object fell. However, we need to account in the real world for things like signal processing delays. All signals take time to get from one point to another. So if you want to time something by waiting to hear when an object lands, you need to account for the time that that sound took to travel from where the landing happened to your ear. Even using our eyes, there still is a little bit of time delay between when something truly happens and when the light gets to our eyes. Now, in the case of a room, that time is nanoseconds. It's imperceptibly small. But for sound, even over relatively short distances, there can be a noticeable delay in the time that sound arrives from when it was sent. So, to factor that in, we still say the object fell starting at rest. It's still subject to gravity, so the free fall acceleration is negative 9.8 meters per second squared, and there still is an observed time of 7.5 seconds from when the object was released to when the reflection of sound from the drop reached the observer's ear. Well, that time, though, is the time for the sound to travel plus the time of the fall. So the time for the sound to travel is the distance that sound had to travel divided by the speed of sound. Since sound travels at a constant speed, and in air it's about 340 meters per second. Now, we also have to have the time of the fall. And the time of the fall from rest through kinematics is going to be the square root of 2 times the distance the object fell divided by the strength of gravity. So that means our total time of 7.5 seconds, which is our known, equals our unknown distance divided by the speed of sound, which is known, plus the square root of 2 times that unknown distance divided by the strength of gravity, which is also a known. Now, if we want to solve for this equation looks messy, but we could rearrange it to solve for delta y, and what we end up doing is getting a quadratic equation. So the first thing I'd do is subtract this term for the time of the sound from both sides. So my total time minus the time of the sound, the distance over the speed of sound, equals the time of the fall. And then if I square it, I have the time of the fall squared, which is 2 times the distance divided by the strength of gravity, is equal to the total time minus the distance over the speed of sound, that whole quantity squared. So, if I multiply out all of the terms, distribute everything, and then rearrange it to get the quadratic equation, my unknown term squared, my distance squared, divided by the speed of sound squared, minus my distance times 2 times the quantity, the total time over the speed of sound, plus 1 over the strength of gravity, plus my total time squared equals 0. So to use the quadratic equation, my value for A is going to be 1 over the speed of sound. And I wrote out these constants to 3 digits. You're going to need to use as many digits as you can in your calculator, or else your answer can vary wildly. So 1 over 340 meters per second quantity squared is our value A. Our value B is negative 2 times the quantity of 7.5 seconds divided by 340 meters per second plus 1 over 9.8 meters per second squared. So, this second term has units of seconds squared per meter, and it's going to be about negative 0.2481. And my final term C is my time squared, which is 56.25 seconds squared. So, in order to solve this problem, we're going to need to use the negative solution, because the positive solution gives us a massive answer in terms of the total distance of that object, and that answer just doesn't make any physical sense. Now, if I subtract the two, I take negative b minus the square root of b squared minus 4ac, and then divide by 2 and a, and I end up with a distance of 228 meters. Now, before, I got a value that I rounded to 280 meters. It was actually like 277 meters. So we're talking about a little over a 20% error at that distance, ignoring the signal travel time in our calculation. So travel times, all of these additional details that are out there and part of the act of measuring, can and always are essential pieces to consider if we want to make a high precision, low error calculation and observation of the real world. Thanks for watching.